In this video, we'll talk about constrained optimization. Constrained optimization is when your problem for optimization has more than one x variable, more than one input. And so you can't just do your regular take the derivative, set it to 0, because there's two x variables that you have to choose between taking the derivative from, right? And so, long story short, the way to do constrained optimization, one way to do it, the way that I'll talk about in this video, is called the substitution method. And essentially, it's exactly what it sounds like. You basically substitute out for one of the two variables. So you need to be given this thing called a constraint equation. So you have the objective function, it's what it's called. It's the thing that you want to maximize or minimize. And then you have this constraint equation, and you're going to use that equation to reduce the number of variables in your main equation that you're trying to optimize. So let's do an example problem. Let's say that you have 100 meters of fencing available for a rectangular lot, right? So there's 100 meters of fencing, and oh yeah, you get to choose basically the dimensions. What should the length be, and what should the width be of your lot? And you have 100 total meters of fencing. But one of those four sides will be provided for by the government. The government's going to pay for one of the four sides. So the question then is, what length and width should you choose to maximize your area? And now this problem might seem like a lot, like you need to know a lot more background information than you do. But really, all you need to know is the area of a rectangle, is length times width. So let's start there. So one thing here, first of all, is being able to take ownership over the problem and be comfortable just labeling variables that they don't even define any variables here. So part of what you have to do here is just, define variables. So what I'm going to do first is kind of draw a picture. And so let's say, all right, if this is the, dimensions, and I'm just going to call them length and width, I'm going to call this W, and I'm going to call this L, length times width. So now, first of all, whatever, I get to choose a value for length, and I get to choose a value for width. And whatever I choose, once I choose them, the area is going to be length times width, right? That's what this area is going to equal. So in general, we have area A equals L times W. And so again, this is called your objective function, because that's the function that you want to try to maximize or minimize. But the problem here is there's two x variables. There's L and W. So you can't just take the derivative of area and set it to 0. So you don't know if you should take it with respect to L or W, and then once you do that, what you do with the other variable. So we need this other constraint, some sort of constraint on us. And that constraint here is that we have 100 meters of fencing available. Now, if that's all that there was, 100 total meters of fencing would just mean that literally L plus W plus L plus W, that those four have to add up to be 100. But the government is going to provide for one of those four sides. We don't know which one. And really, it doesn't really matter which one we call length or width. Those are sort of arbitrarily chosen anyway. So let's just say that the government's going to provide one of the W sides for us, right? And again, it doesn't matter. Even if we called it W, we could just, rotate it. It really doesn't matter which one we're calling, because, it's all the same in space. So in either case, let's say that the government's going to provide one of these two sides. So really, our fencing, our 100 meters of fencing, really only applies to L, W, and this other L. So our constraint equation, again, it seems like you might need to know some sort of background knowledge from the world, but no, you just need to be able to translate English to math. And here, if L plus W plus L, if these three side lengths have to add up to 100 meters, all that's saying is literally L plus W plus L equals 100. So the constraint equation is literally length plus width plus length. Those three sides have to add up to 100, the three sides that we're going to pay for. And like terms, L and L simplify to 2L. So you can further say this is just W plus 2L is 100. So this is what we call the constraint equation. And like I said, a hard problem, like this one, a hard problem, is just one where you have to come up with the constraint equation. But a problem might just, an easier version of this problem would have just started with, suppose W plus 2L is 100, you want to maximize this function, L times W, go for it. So in either case, even if it starts with just a paragraph, once you translate what your constraint is and what your objective function is, now the process is really simple. just literally solve for one of the variables here. It doesn't matter which one. We can be strategic, but it doesn't matter which one. You solve for one of them, and then plug that back in here to reduce the number of variables here down to just one x variable. So strategically, just fractions-wise, it's probably going to be better if I want to do less division to solve for w instead of L. So to solve for w, that way I don't have to divide by 2, I could just subtract 2L from both sides, so I get w is 100 minus 2L. And now that I have that, I can replace this w with using the constraint equation. So that makes my area equal to length times width, but width is really 100 minus 2L. So again, this is the thing that I substituted in from the constraint equation. And now that I have that, I can even simplify this as area equals just distributing 100 times L is 100L, minus L times 2L is 2L squared. And so now I have it down to a really simple quadratic equation that I can optimize the regular way, take the derivative, set it to 0. So the derivative here, the first order condition tells me that the derivative of this is, let's see, the derivative of 100L is 100, minus and the derivative of 2L squared is 4L, and the first order condition sets that equal to 0. So to solve for this, I could just add 4L to both sides, so 100 equals 4L, and then divide by 4, so 100 over 4 is 25, so I get L equals 25. And here, if you want it to be safe to make sure that you're maximizing the area, not minimizing it, we could check the second order condition, the A double prime. So that's the derivative of this first derivative. So if this is the first derivative, the second derivative would be, let's see, the derivative of 100 is 0, and the derivative of negative 4L is negative 4, so the second derivative is negative 4, which means we don't even need to bother plugging this in because this is always going to be concave down, as in if the second derivative is negative, your area is always going to be concave down, which means that the critical point must have been a maximum rather than a minimum. So the second order condition satisfied, so SOC, that's the second order condition for a max rather than for a minimum, right? Because it's negative. So we have our second order condition maximized and we found the length. So going back to this problem, this means that the length needs to be 25. So this is 25 and this is 25, which, given that these three have to add up to 100, we can easily find the W. We don't even need to do any thinking there. We could just literally go back to the constraint equation. In fact, the simplified version of it literally outputs what our W will be once we found our L. So our W, just using this here, W equals 100 minus 2L, but L we just found is 25. So 100 minus 3 times 25 is 50, so 100 minus 50 is 50. So W is 50. All right, so that's 50. And so overall, the answer to this question is that in order to maximize your area, out of the three sides that you choose, doesn't matter, again, the L and the W is sort of irrelevant which is which, just out of the three sides that you're picking, two of them are going to be 25, and the other one, the third one, is going to be 50, and that's the one that the government's going to match. And this might seem like, how is this sort of relevant for most real world, like even public policy type applications, if this seems like a farming problem, like lot and stuff. But the principle here is sort of that if the government is subsidizing something, then it's probably in your best interest instead of just, if the government wasn't subsidizing anything, if you did that version of it, you'd find that the optimal area is just to set 4 equal sides. So basically having a square lot is the optimal. But if the government's doing something, it's going to be in your best interest. It seems obvious to most people, but this is the math proving that the way to optimize things, if the government's paying for something, is to basically, it's going to change your priorities compared to if the government's not doing it, right? So it's going to matter. You're basically getting more bang per buck out of having a longer width because the government's matching that. So in this case, again, it has some policy implications as far as the subsidy changes the optimal decisions for people. So now let's do a totally different question. The demand for MC schools rap songs are given by this equation over here. Sure. And if the production cost of Q rap songs is given by this equation over here, then the question is how many rap songs will maximize profit? So again, the background, the only economics that you need to know for this is the equation for profit, which is revenue minus cost. And specifically that revenue is price times quantity. And that, you could use this as for price, and this Q is quantity. So let's first set that up. So in most economic applications, we're going to have that. Let's write this here. So in most economics applications, we're going to have our profit given by the variable pi, right? So the profit is going to be pi. And again, it's just that we use pi because we've already used P for price. The equation for profit again is price is equal to P times quantity. Price times quantity minus your cost, right? Revenue minus cost. Pretty straightforward. And further, let's plug in stuff here. So P times Q minus, we're given the cost. The cost is this guy, Q squared plus 50Q. So if we use that constraint equation and plug that in here, we get that this is minus, use parentheses, Q squared plus 50Q. And heck, we could even, distribute that negative, so we could say our profit is PQ minus Q squared minus 50Q. So really, this is, again, just to recap, our revenue that we bring in minus our cost, right? So, but even still, we're still not done substituting from our constraints because we have two variables, P and Q. So is there a way to substitute out P? Well, the only other info we have is this other constraint equation. And so now notice, so here's where strategy kind of matters. One thing you could do straight up is you could literally just, it's already solved for a Q. You could just replace the Q here. And there's three Q's here, this guy, this guy, and this guy. You could replace all three of those with 100 minus half P squared. And then you have just P as a variable here. You already have this one P, but then you'll have three other P's that show up. And then you just have P, and then you can take the derivative, set it to 0, and you find the price. And then you can plug that, once you find the price, plug it back in here to get the Q. And that'll give you the quantity of rap songs that should be produced to maximize profit. But strategically, if you don't want to have to substitute for three different places, if you'd rather only substitute this one P out, then, this one P out, then it's better to solve for the P here instead of the Q here. So let's solve for this P so that we can substitute it out. So here, if I were to solve for the P, I guess I would add half P to both sides. So I get half P on the left-hand side, and I would subtract Q, so equals 100 minus Q, right? So I just added this, subtracted that. Then I could multiply both sides by 2, so I get P equals 200 minus 2Q. All right, so now that I got P, I could now write the profit equation. I'll write it here as profit equals P, which is, using this guy, 200 minus 2Q, price times quantity, minus this cost, so minus Q squared minus 50Q. So really, again, all we did here was we substituted out from the stuff that we were given. So from all the stuff, we set up the profit equation, the thing that we want to maximize, using the stuff that was given, using the only economics knowledge was the same economics that somebody running a lemonade stand would know, which is, oh yeah, price times quantity is my revenue, and minus my cost, that gives me how much money I have in profits. So that alone, and just substituting things out, gives us this equation which only has a Q in it as a variable, and now we can optimize by taking the derivative, setting it to 0. So here, if we take the derivative, so here's a little pro tip. Take your time before you take your derivative. So if you try to take the derivative here, there's a big chance that you make an algebra mistake. And so what I would personally do is I would just try to FOIL it out as much as possible, because that way you avoid having to do the product rule with the negatives. It's just, our human minds, it'll make a careless mistake one in every so many times. And so to try to avoid that, you might as well not ask yourself to do things that will, where you're likely to make those type of mistakes with things like the product rule or have with the negatives, distributing with negatives. So what I'll first do is I'll just simplify this as much as possible. So distributing this guy, I get 200Q minus 2Q squared, right? Distributing the Q to those. Then I have minus Q squared minus 50Q. And I'm going to go one step further, I guess this is good enough. The only other thing we could do which maybe we should. Yeah, let's just go one step further here. Let's just really take our time before we take this derivative. Let's simplify like terms. We got 200q minus 50q, which is 150, right? 200 minus 50 is 150q. And then we have minus 2q squared minus another q squared, so overall that's minus 3q squared. So that's a much nicer looking profit equation, right? So notice, this problem is essentially, with the info that they gave you, they basically are saying, here's your profit, maximize it, meaning take the derivative, set it to 0. So if we take the derivative to get the first order condition, the derivative of 150q is 150, minus the derivative of 3q squared is 6q, and so we set that equal to 0, and then we could just solve for q. We can add 6q to both sides, so we get 150 equals 6q, and then divide both sides by 6, and I guess we get 25. 150 divided by 6 is 25, so yeah, so we get 25 equals q. So MC School should make 25 rap songs in order to maximize profit. But wait, do we know if it's maximizing or minimizing? Let's take the second derivative to find the second order condition. And so if 150 minus 6q is your derivative, your second derivative is going to be, let's see, the derivative of 150 is 0, and the derivative of minus 6q is just minus 6. Oh yeah, so the negative second derivative means that you're maximizing, so you're all set. And again, if this was positive, that means you would have been minimizing your profit. Which, hey, sometimes for some problems like minimizing cost, you want to minimize, and so you want the second derivative to be positive. But anytime you want to maximize something, you want to make sure that your second derivative is negative. And again, here, the second derivative was already negative. We didn't even have to plug it in. But if this still had like a q in it somewhere, you want to make sure it's negative even after you plug in that critical point of q is 25. Final problem we'll do in this video. Suppose u, utility, is equal to this. So again, here, let's just do this where even if we know no economics, no background, this is just the pure math problem. Suppose u is equal to this thing. So it's based on these three variables here. There's u, x1, and x2. Those are the three variables. And then here we got this constraint equation with the two of the variables. So in either case, we want to maximize this guy, and we know we have this as a constraint, right? So what values, the question is what value of x1 and x2 do we need to choose in order to maximize u? So instinctively, if a question just says maximize u, you're thinking, all right, take the derivative, set it to 0. What's the problem? There's too many variables here. There's an x1 and an x2, and so, we need to basically reduce the number of variables. And the way we can do that is by using a constraint equation. So using this constraint equation, an equation that has to be true, we could basically swap out. And so here's the thing. You could solve for x1, right? Strategically, you'll end up dividing both sides by 6 when you do that, right? To solve for it, let's just think 2 steps ahead. I'd subtract 2x2, and then I'd divide by 6, and then that's not going to cancel out because 2 over 6, that's going to be 1/3. Not only that, once I do that, that's x1, so then I'm going to plug it in here. So when I plug it in there, my utility function is going to be that thing that I plugged in squared. I mean, that's like, 90 over 6 minus, 1/3 x2. It's like squaring that, and then, so it's like, it's going to be a lot. So instead, strategically, so you could just instead solve for x2, because then you're plugging it into this guy. You're plugging it into something that's not going to then get squared before you take the derivative. So just to minimize the number of steps, strategically, I'm going to solve for x2 here. So here, to solve for x2, I subtract 6x1 from both sides. So this becomes 2x2 equals 90 minus 6x1. Then finally divide both sides by 2, and I get 45 minus 3x1. Much cleaner. And now I can plug that into this x2. So my utility equation becomes u equals x1 squared times x2, which x2 is now 45 minus 3x1. And so if I were to distribute that out, I get 45 x1 squared minus, let's see, I have 3x1 times x1 squared, that's going to be 3 x1 to the third power. And so now if I take the derivative, my first derivative condition, I get 45x1 squared. The derivative of the 2 comes down, so I get 90x1 to the first power, minus, the 3 comes down here, so 3 times 3 is 9, 9x1 squared, and I set that equal to 0. Now to solve for that, I could factor out a 9 from both sides. I can also factor out an x1 from both sides, and then I'm left with 10 here, minus x1. Let's just make sure we did that right. If we distribute this, 9x1 times 10 would be 90x1, and 9x1 times negative x1 would be 9x1 squared. All right, so we did that right. And now quadratic, so here the solution is that x1 is either 0 or 10 minus x1 is 0, which means x1 is either 0 or x1 is equal to 10. So basically, because you basically have 10 minus x1 equals 0, add x1 to both sides, so x1 is 10. So these are your two critical points. And so for each of these critical points, you could then check to see what x2 would have to be. Or I guess first, instead of both, let's first figure out, is one of them a max and one of them a min? What's going on? So for that, we could find the second derivative. For the second derivative, for the second order condition, the second derivative, let's see here, is going to be 90 minus 18x1. So how did I get that? The derivative of, because this is the first derivative, so the derivative of that is, so the derivative of 90x1 is just 90, and the derivative of negative 9x1 squared, the 2 comes down, so that's why I get the 18, and the derivative then of just x1 is x1 to the first power, right? So again, that's just like that. And so again, for the second order condition, we don't set that equal to 0. We simply check if this is positive or negative. So let's see, if x1 is 0, so the u double prime of 0, if x1 is 0, then this is 90 minus 0, so then that's 90. And if the second derivative is 0, that means that your function's concave up, which means that the original function is at a minimum if you're at a critical point, right? So here, so this we can eliminate as a maximum because that minimizes here, versus the second derivative at 10 is going to be, if x1 is 10, 10 times 18 is 180, and 90 minus 180 is negative 90, so that's negative, so this maximizes. So this, a negative second derivative, is the second order condition for a maximization. If this question had said minimize utility, then this would be our answer. Our answer would be that 0 is the appropriate value for x1, and we would eliminate 10 because that would maximize it, not minimize it. But here we want to maximize, so our answer is that x1 has to equal 10. The question asks for x1 and x2, so to get x2, we can just go back to the last version of our constraint equation. Notice a lot of people then go back to the original constraint equation, plug in x1 is 10 and solve for x2. But you can shave off a few steps because you've already simplified the constraint equation all the way down to this, where x2 is by itself on one side. So you might as well use that and say, all right, 45 minus 3x1, where x1 is 10, and then simplify that. So that's 45 minus 30, which is 15. So our final answer here is that in order to maximize u, you got to set x1 equal to 10 and x2 equal to 15.